I welcome you all for the lecture on the thermodynamic aspects of Otto Cycle. And the internal combustion engine, namely the petrol engine, works on the principle of Otto Cycle. The petrol engine is otherwise known as spark ignited engine. So let us have the thermodynamics part of the Otto Cycle. In the thermodynamics part of the Otto Cycle, we have the PV diagram and the corresponding TS diagram. So it is pressure volume. The suction stroke, in the suction stroke, the petrol and the air mixture will be entering the combustion chamber from the carburetor, which is indicated by a horizontal line 0 to 1 at full throttle condition, and 1 to 2 is nothing but the compression stroke, which is aided by isentropic compression process, otherwise called as reversible adiabatic process, and hence I can indicate this as the entropy remains constant. And the process 2 to 3 is nothing but the heat addition, which takes place at constant volume. So this line should be straight line, is a vertical line. So this point 2 to 3 is nothing but the heat addition, which is taking place at a constant volume. So during the power stroke, the piston will be moving from the TDC to the BDC because of the expansion of the gaseous mixture, combustible mixture, which is given by 3 to 4. 4 to 1 is once again a constant volume heat rejection, which is given by QR. This process 3 to 4 is also isentropic in nature, that is isentropic expansion takes place in the engine cylinder. The corresponding TS diagram, I can draw the corresponding TS diagram. Temperature entropy diagram. The process 1 to 2 is nothing but the isentropic compression. So it is a vertical line, and the process 2 to 3 is nothing but constant volume heat addition. Because of this, a temperature, there will be a huge rise in the temperature. So the point is 3, the heat has been added, and here it is nothing but constant volume process. And the process 3 to 4 is isentropic expansion, so it should be a vertical line. So the point 4 is there, and 4 to 1 is once again the heat rejection, which takes place at constant volume. In a cycle, we know that the summation of the heat transfer should be equal to the summation of the work transfer, and hence this PV diagram and TS diagram looks identical. Whereas in the actual case, we know that all heat can be converted to work because of the limitation of the circle of thermodynamics, and hence this diagram will be bigger compared to the PV diagram. Let us now derive the efficiency of this particular Otto cycle. This Otto cycle is also nothing but a heat engine. This executes a heat engine because we can see there is a heat addition, there is a work done by the piston, there is a heat rejection. So it's nothing but a heat engine. A heat engine is a device which takes heat as input and delivers mechanical work as output. So I can derive, or I can tell, the efficiency of any heat engine is defined by mechanical work by heat input or heat supply. So we know that in a cycle, the summation of the heat transfer will be equal to the summation of the work transfer, and hence this work can be replaced by the summation of the heat transfer. So the summation of heat transfer is nothing but heat supplied minus heat rejected. And the heat supplied is given by Qs. Because this executes a cycle. We know from the first law of thermodynamics, the summation of the net heat transfer will be equal to summation of the net work transfer. Based on that, we derive this formula. And when I am going to do the mathematical simplification, it will become 1 minus Q watt by Qs. This is the efficiency of any heat engine. Since this Otto cycle also executes a heat engine, we can utilize the same formula for the Otto cycle also, which is nothing but 1 minus Qr by Qs. So I want to know what is meant by Qr and Qs. So generally heat is given by mCp delta T or mCv delta T. Here the heat rejection 4 to 1 as well as the heat supply 2 to 3, both are happening at a constant volume process, and hence the formula for Q will be mCv delta T. If I want to see Qs, is nothing but the heat supplied to the constant volume process. So Qs will be equal to mCv into T3 minus T2. The heat is supplied between the process 2 to 3. From the TS diagram, you can see that T3 is higher than T2. So Qs will be equal to mCv into T3 minus T2. We are taking only the magnitude, and the dash will be taken care by this formula. And the heat rejection Qr, you can see the heat rejection is taking place in the process 4 to 1. So Qr is nothing but once again mCv into T4 minus T1, because the 4 temperature will be higher than the temperature at the point 1. So it is T4 minus T1. If I can keep this equations 1, these 2 are 2 and 3. Now substitute the value of 2 and 3 in 1. We will derive the equation for the efficiency. Substituting substituting 2 and 3 in 1. The efficiency of R2 is given by 1 minus mCv into T4 minus T1 divided by mCv into T3 minus T2. So I can cancel off m and specific capacity at constant volume. So finally the formula for Otto cycle ends up with 1 minus T4 minus T1 divided by T3 minus T2. So this is the formula we derived for the efficiency of the Otto cycle in terms of the temperature T1, T2, T3, T4, which says that T4 should be less. On the other hand, this is not given a complete idea, so we are going to derive the formula for efficiency of Otto cycle in other terms, especially R and gamma. R is nothing but the called as the compression ratio, and gamma is nothing but the ratio of specific capacities is nothing but gamma equal to Cp by Cv. Let us proceed further to derive the same. Okay. Now for the isentropic compression process 1 to 2. We also know that isentropic is nothing but reversible adiabatic process. So generally the adiabatic process is governed by the following equation: P equal gamma equal to constant, where gamma is nothing but the ratio of specific capacity, where gamma is nothing but Cp by Cv, where gamma is nothing but Cp by Cv. Now the same can also holds good like this. P1 V1 power gamma equal to P2 P2 power gamma. Since it's an adiabatic process. We also know, and we are going to assume that the fluid mixture or the air mixture is going to be as an ideal gas, which means we can invoke the equation PV equal to MRP. And this equation can be applied for all these 8 points, namely 1, 2, 3 and 4. So let me utilize for the points 1 and 2. So P1 V1 equal to MRT1, P2 V2 equal to MRT2. Let us have this is equation number 5, this is 6, this is 7. So from 6, V1 or P1 is equal to MRT1 by V1. Similarly from 7, P2 will be equal to MRT2 by V2. So substitute the values of P1 and P2 in 5. Substituting values of P1 and P2 in 5, we get. So it is MRT1 by V1 into V1 power gamma is equal to MRT2 by V2 into V2 power gamma. For time being, I will write this equation separately so that we can utilize in future. The efficiency of Otto is given by 1 minus T4 minus T1 divided by T3 minus T2. It will be here. I will erase for the time being. It is equation number 4. So from this, simplify further. So M can get cancelled, R get cancelled, and we have T1 into V1 power gamma by V1. Similarly here T2 into V2 power gamma by V2. So this V1 is having a power of 1. This V2 is also having a power of 1. So I am going to do some mathematical simplification. T1 into V1 power gamma minus 1. Because I am having a power of gamma, I am going to take the denominator to the numerator. This plus 1 becomes minus 1. So T1 into V1 power gamma is 1. Similarly, T2 into V2 power gamma minus 1. From this, I want to find what is T2 by T1. So T2 by T1 will be equal to V1 whole power gamma minus 1 divided by V2 power gamma minus 1. From the simplification, T2 by T1 will be V1 by V2 whole power gamma minus 1. And here we have to define an important parameter which is known as the compression ratio. It is nothing but R. R is nothing but V1 by V2 is given by a term called as compression ratio. For this, it is better to draw the piston cylinder assembly so that a better idea can be obtained. So this is my piston cylinder assembly. This is my piston and this is the cylinder, and this portion is called as my BDC. Here BDC refers to bottom dead center, and the piston can move to the top, and it can't go and hit the topmost cylinder head. It has to stop well before that, and let us say its new position is here. And this position is called as TDC. So the TDC stands for top dead center. When the piston is occupying the position at BDC, the corresponding cylinder volume is called as V1. And when the piston is going to occupy the volume at TDC, the corresponding volume is called as V2. The corresponding volume is called as V2. And always you have to give a small volume, it should be cleared up without hitting the cylinder head. And hence this V2 is otherwise called as VC, which is nothing but called as clearance volume. Generally this volume has been left out because we have in case of 4-stroke engine, we have this inlet valve and the exhaust valve. This valve has to move inside. So we have to take enough measure that this valve will not come and hit on the piston when it is going to reach the TDC. So that is the reason why we are giving this clearance volume. And in case of petrol engine, we will have a spark plug. So this one is called the spark plug. And these are nothing but the inlet valve and the exhaust valve. Now, if I am going to take the volume as V1 by V2 is nothing but by R. R is nothing but the ratio of V1 by V2. We can see that the volume V1 is very high or big compared to the volume occupied by the piston activity, which is V2. So V1 by V2, generally this value will range from 6 to 10 for petrol engine and it will vary from 60 to 20 for diesel engine. And since this Otto cycle we are going, the maximum value of R can be restricted to 10. Maximum value. So it ranges from 6 to 10. So we should know what will be R is nothing but how much we can compress the petrol air mixture at the end of the compression. That is the logic. Here I want to give a small note about this IC engine also. During the inlet stroke, there are 4 strokes. If I am going to consider a 4-stroke petrol engine, there are 4 strokes. The first stroke is inlet stroke or suction stroke. The second one is compression stroke. The third one is called as power stroke or expansion stroke or working stroke. And the 4th stroke is the exhaust stroke. Stroke is defined as nothing but the movement of piston either from TDC to BDC or from BDC to TDC, either way. And in case of the petrol engine, during the suction stroke or the inlet stroke, the inlet valve remains open. So when we are going to make this valve to push down, there will be a clearance will be happening so that the petrol and the air from the carburetor after enough mixing will be entering to the combustion chamber through the inlet valve. During this stroke, the exhaust valve remains closed. The exhaust valve remains closed. And the piston will try to move from the TDC to BDC, creating more vacuum, and hence there is a flow of petrol and the air mixture into the combustion chamber. So in the suction stroke or the inlet stroke, the petrol and the air mixture enters into the combustion chamber via the inlet valve. The piston moves from the TDC to the BDC, and the exhaust valve remains closed. This completes the inlet stroke. And coming to the combustion stroke, during this stroke, both the inlet valve and the exhaust valve remains closed. The piston will be moving from the BDC to the TDC, compressing the petrol air mixture. Compressing the petrol air mixture. When the piston is going to reach almost the TDC, a spark will be given from the spark plug. So at the end of the combustion stroke, a spark will be given from the spark plug. That will initiate the combustion. The heat transfer will take place at we assume that the heat transfer takes place at a constant volume. So that is nothing but the combustion stroke. During this combustion stroke also, both the inlet valve and the exhaust valve remains closed. Coming to the power stroke, during the power stroke, because of the combustion taking place between the petrol and air, because of the spark ignited, the mixture will try to expand. Since all the valves are fixed, the only possibility is that it can move the piston downwards from the TDC to the PDC. This is nothing but called the expansion stroke or the power stroke because work is done by the system on the piston. And hence is considered to be positive. During this stroke also, both the inlet valve and the exhaust valve remains closed. So that is nothing but the working principle of the power stroke. In the power stroke, because of the expansion, because of the combustion, it gets expanded and move the piston from TDC to BDC. Both the inlet valve and exhaust valve remains closed. Coming to the final stroke called the exhaust stroke. During this stroke, the exhaust valve should remain open, and the piston will be moving from the BDC to the TDC, expelling the exhaust gases into the atmosphere. Exhaust gas into the atmosphere. So automatically we know that inlet valve should remain closed and the exhaust valve should remain open, and these gases will be going into the atmosphere. So this completes the four-stroke of the petrol engine. And coming to the diesel engine, if you want to have the same thing for diesel engine, the only difference is during the success stroke, both petrol and air will have come, or both diesel and air will have come. Only the air will be entering into the combustion chamber, and there is no need of any carburetor. Only the air will be entering into the combustion chamber. The piston once again moves from the TDC to BDC. The exhaust valve remains closed. During the combustion process, only the air gets compressed. Only the air gets compressed, whereas the combustion ratio will vary from 16 to 20 for diesel engine. And this spark plug can be replaced by fuel injector. At the end of the combustion stroke, the fuel will be sprayed at very high pressure, ranging from 200 bar to even 1500 bars. And hence, because of the high compression, the fuel gets auto-ignited. And once again, the working principle of the power stroke and the exhaust stroke remains same as that of the petrol engine. So this is the small difference between the petrol engine and diesel engine. The difference is, during the suction stroke, only the air gets in, and the compressed stroke also, only the air gets compressed. And at the end of the compression, the fuel will be sprayed from the fuel injector. So that completes you the diesel engine. Now we will have a better idea of what is meant by compression ratio, what is meant by the value of compression ratio for petrol engine and diesel engine, what is known as BDC, TDC, what is meant by stroke, all these things. So now coming to the thermodynamics aspect of the Otto cycle, this R is nothing but V1 by V2. I can replace this V1 by V2, which is nothing but compression ratio, by R. So T2 by V1 is nothing but R raised to the power of gamma minus 1. You will take care such that you should have to differentiate between R and gamma. So far there is only gamma, now we have R also. So you have to differentiate between R and gamma carefully. So this T2 by T1 equal to R power gamma minus 1. Let us have, this is equation number, I hope you can have it saved. So we have found a relationship between T2 by T1 in terms of R and gamma. Similarly, now the process 1 to 2 is compression. The same process is happening from 3 to 4, but instead of compression we have expansion. So this is also isentropic in nature, which is nothing but reversible adiabatic. For reversible adiabatic process 3 to 4, here also P3 power gamma equal to constant, which means P3 V3 power gamma equal to P4 V4 gamma. I don't want to repeat once again. That is, you want to substitute the P3 and P4 from ideal gas equation PV equal to MRT. That is P3 V3 equal to MRT3. So from this P3 equal to what? MRT3 by V3. Similarly, P4 will be equal to MRT4 by V4. Substitute the value of P3 and P4 in this equation. Finally, if you are going to present the same way what we have discussed, we will end up with what? T3 by T4 will be equal to V4 by V3 whole power gamma minus 1. How means? Here we have T2 by T1 is nothing but equal to V1 by V2 whole power gamma minus 1, isn't it? So now the temperature and the volume are inertial proportion to the power raised gamma minus 1. Similarly, here also have a temperature but should be inversely related. So T3 by T4 will be equal to T4 by V3 whole power gamma minus 1. So what is V4? V4 will be equal to V1 from this PV diagram. And what is V3? V3 will be equal to V2 from the diagram. So we can see that T3 by T4 is nothing but V1 by V2 whole power gamma minus 1. How I got this one? From PV diagram. From PV diagram we can see that V4 equal to V1 and V3 equal to V2. Let us start this as equation number 9. So once again, what is this T3 by T4? T3 by T4 will be equal to R, because we know that V1 by V2 is nothing but combustion ratio R, rise to the power of gamma minus 1. From 8 and 9, since the right hand sides are equal, R for gamma minus 1, it is well known fact that the left hand side should also be equal, which is nothing but T2 by T1 will be equal to T3 by T4, which is equal to R power gamma minus 1. So I am comparing equation number 8 and 9 and finding that T2 by T1 will be equal to T3 by T4, which is equal to R power gamma minus 1. If I am going to take the inverse or reciprocal, T1 by T2 will be equal to what? T4 by T3 will be equal to what? 1 by R power gamma minus 1. So I am taking the reverse reciprocal of all the terms. So T1 by T2 will be equal to T4 by T3 equal to 1 by R power gamma minus 1. Let us have this is equation number 10. We can even write like this, nothing wrong in that. T4 by T3 is equal to T1 by T2 equal to, from 10. Or if you want, you can take this also, 1 by R power gamma minus 1. From this one, T4 by T3 is equal to T1 by T2 implies this should also be equal to T4 minus T1 by T3 minus T2. This is a common rule in mathematics. So if T4 by T3 is equal to T1 by T2 means, then T4 minus T1 by T3 minus T2 will also be equal to what? T1 by T2 and T4 by T3. For example, if you want to make a confirmation of this one, if I am going to have T4 as 100 and T3 as 20, the ratio will be 5. Here also you can take 10 by 2, then also will be 5 because both will be equal. Now you can take 100 minus 10 by 20 minus 2, which will be 90 by 18, which will also be equal to 5. So which implies that when T4 by T3 equal to T1 by T2, then I can tell this ratio T4 minus T1 by T3 minus T2 also will be equal to either T1 by T2 or T4 by T3. And also we know this value is equal to 1 by R power gamma minus 1. Also we know that this T1 by T2 equal to 1 by R power gamma minus 1. So this is very, very important equation. So keep it as number 11. Now we will recall or we will recap that the efficiency of Otto cycle is given by 1 minus T4 minus T1 by T3 minus T2. So substitute for T4 minus T1 by T3 minus T2 from 11 in terms of R and gamma. So I will end up with, I hope I can erase this one. I will end up with efficiency of Otto is given by 1 minus 1 by R power gamma minus 1. So I got this one by substituting 11 in 4 vehicle. Efficiency of Otto is nothing but 1 minus 1 by R power gamma minus 1, where R is nothing but V1 by V2 and gamma equal to Cp by Cv. So we found it is independent of your temperatures T1, T2, T3 and T4, and it depends mainly on two parameters, namely the combustion ratio and the ratio of the specific capacity. We can also explain this one with a small graph. So in the y-axis, I can take the efficiency. In the x-axis, I can take the compression ratio R. Gamma equal to 1.3, gamma equal to 1.4, gamma equal to 1.67. This gamma equal to 1.3 is obtained for exhaust gases. Gamma equal to 1.4 is for air. And gamma equal to 1.61 for monoatomic gases. So from this relationship, we can see that if I am going to increase this denominator or compression ratio, this value will come down, so my efficiency will increase. Which means that if I am going to increase the compression ratio, my efficiency will increase. So that is, we can see this graph. When I am going to increase the compression ratio, the efficiency is getting increased. Or either gamma 1.3 or 1.4 or 1.6. The same trend is obtained. Which means that when I am going to increase the compression ratio, my efficiency also increases. The second parameter is gamma. Gamma is nothing but the ratio of the specific capacity. If I am going to increase the gamma, the curve will be shifted to the top. The curve will be shifted to the top. That means, if you are going to increase the value of gamma, definitely this denominator is going to increase, this will come down, so my efficiency will go up. So these are the two parameters upon which an ideal Otto cycle works, namely the R and gamma. So anyone's idea should be to increase the value of R and gamma to have the maximum efficiency. And when you are going to study more about petrol cycle and diesel cycle in internal combustion engines, we can see that the value of R is limited to 10 for petrol engine and it can go up to 16 to 20 for diesel engine because of some parameters known as locking, etc. Okay. Let us move further to derive the power produced or the net work done is given by W minus WC. Where W is nothing but the work of expansion which is taking place from 3 to 4, which is positive, and there is a negative work because we are doing work on the system from 1 to 2. So there is WE minus WC. So WE is given by 4 and WC is given by W 1 to 2. And this is nothing but both are adiabatic process. We know that the work done in the adiabatic process is given by P3 V3 minus P4 V4 by gamma minus 1, and this is given by P2 V2 minus P1 V1 by gamma minus 1. From this term, I can take P1 V1 by gamma minus 1 as a common term from all the 4 terms. So the remaining will be P3 V3 by P1 V1 minus P4 V4 by P1 V1 minus P2 V2 by P1 V1 plus 1. Because this minus into minus will become plus 1. Now I will simplify further. P1 V1 by gamma minus 1 into, I am going to multiply and divide by P2, so the answer will not be very much. So P2 by P1 into V3 by V1 minus P4 by P1 into V4 by V1 minus P2 by P1 and V2 by V1 plus 1. Here I want to define one more parameter called as pressure ratio, RP. RP is nothing but pressure ratio, which is nothing but P3 by P2. So how much pressure has been increased when I am going to add the heated constant volume? So it's P3 by P2, which will also be equal to P4 by P1. So P1 V1 by gamma minus 1. This P3 by P2 is nothing but called as the pressure ratio RP, and P2 by P1. We know that P1 V1 per gamma equal to P2 V2 per gamma because it is reversible adiabatic or adiabatic process. From this, if I want P2 by P1, it becomes V1 by V2 whole power gamma, which is nothing but P2 by P1 will be equal to R power gamma. So it is something but P2 by P1, I can replace it R power gamma. And from the diagram you can see that the V3 will be equal to V2. So V2 by V, instead of V3 can be called as what? V2. So V2 by V1 is nothing but 1 by R. So this V3 by V2 is replaced by 1 by R minus P4 by P1, as I told you earlier, will also be equal to Y, pressure ratio of RP. And from the diagram you can see that V4 is equal to V1. So this V4 and V1 get cancelled off. And minus P2 by P1 is nothing but once again my P2 by P1 is nothing but R power gamma, and P1 by P2 will be called as my, or P2 by P1 is called as 1 by R plus 1. So for the simplification, P1 V1 by gamma minus 1 into RP into R power gamma minus 1, because this is having a R power 1, this is having R power gamma. So when I go to take the numerator, it will become RP into R power gamma minus 1 minus RP minus R power gamma minus 1, because this R power gamma is R power 1 plus 1. So I hope I can erase this TS diagram. So it will be P1 V1 power gamma minus 1. For the first term and the third term, I can take R power gamma minus 1 as the common term. So it become RP minus 1 minus the other two terms are RP and this one. From these two terms I am going to take minus 1 as the common term. So the remaining will be RP minus 1. So from these two terms RP minus 1 is common term. So for the simplification, P1 V1 by gamma minus 1 into RP minus 1 can be taken as common term. The remaining will be R power gamma minus 1 minus 1. So this is the formula which is derived for the work done, negative work done or work developed by the Otto cycle. So I can give any expression, maybe 13 or 14. So this is the formula for the work developed by the engine. And one more formula is there. That is, we want to find the mean effective pressure, which is given by PM, which is nothing but work done by swept volume. Here the volume is called as swept volume. The PM will be called as work done divided by swept volume is given by, already we saw in the piston center assembly, is nothing but the movement of the piston from TDC to the BDC. So it is V1 minus V2. Substitute here. Already we know the formula for work done. If I want to know the formula for mean effective pressure, PM will be equal to work done by V1 minus V2. So we know that the mean effective pressure is given by the numerator is nothing but the work done. The denominator is nothing but what? The swept volume. So V1 minus V2 is the swept volume. So this V1 minus V2 can also be written as what? V2 can be taken as common term. So V1 by V2 minus 1 is nothing but V2 into R minus 1. So the denominator can be replaced by V2 into R minus 1. V2 into R minus 1. So this V1 by V2 will become R and gamma minus 1 into R minus 1 into this bracket term. So RP minus 1 into R power gamma minus 1 minus 1. Okay, so this is the formula for the mean effective pressure which is developed in the IC engine. So PM will be equal to P1 into R divided by gamma minus 1 into R minus 1. So this is the value. So this finishes off the thermodynamic aspects of the Otto cycle. In the next session, let us discuss with the diesel cycle, dual cycle and the Petrol cycles. Thank you.